2. First off, I want to make a correction. When I typed up the notes Thursday, my old eyes misread the book when I was typing. And when I wrote 1,000 kilocalories equals 4186 joules, that was totally wrong. It should have been that 1.000 kilocalories equals 4,186 joules. So there is a correction. Okay, first problem. Rubbing your hands together warms them by converting work into thermal energy. If a woman rubs her hands back and forth for a total of 10 rubs, a distance of 7.5 centimeters each, and with a frictional force averaging 45.0 newtons, what is the temperature increase? The mass of tissue warmed is only 0.1 kilograms, mostly in the palms and fingers. As always, when confronted with a problem, even if you're not sure what to do, go ahead and write down what you know and what you're hunting for. So you rub the hands back and forth 10 times. Each time it was 7.5 centimeters. The force is 45.0 newtons. The mass is 0.1 kilograms. And we're hunting for the temperature increase, or delta T. And we've got a formula with delta T in it, Q equals MC delta T, but that doesn't help a whole lot because we have an M, but we don't have a C, we don't have a Q, so you're not sure. But remember from the notes before, there's no real way to determine how much heat an object is, just like we can't tell how much work an object has. Instead, we measure how much work is done by or done on an object. Likewise, you measure how much heat is transferred to or from an object. This is called heat transfer, or Q. And conservation of energy tells us that the heat transfer is the same as the work done, which then gives us the idea of calculating work, which we can do. Work equals force times distance. To calculate the distance, D equals 10. 10 times she did it. 7.5 centimeters each time, 75 centimeters. Changing it to meters, 0.75 meters. So the work done is 45 newtons times 0.75 meters, or 33.75 joules. Work done is equivalent to the heat transferred. Conservation of energy. So now we have the work done, and we also have heat transferred. So we've got Q, so we can go ahead and put that into the formula. Q equals MC delta T, which gives us a delta T of 0.096 degrees centigrade or Celsius. Notice in this equation I actually put down the units because it's gonna be tricky, and I don't want to screw up my units. I want to make sure I've got joules and joules, I've got kilograms and kilograms, so I'm putting them in, even though generally I don't like to do that, but I'm afraid I'm going to make a unit mistake otherwise. Next one up. Even when shut down after a period of normal use, a large commercial nuclear reactor produces heat at the rate of 120 megawatts by the radioactive decay of fission products. This causes a rapid increase in temperature if the cooling system fails, like it did in Japan and 3 Mile Island. A. Calculate the rate of temperature increase in degrees Celsius per second if the mass of the reactor core is 1.6 times 10 to the 5th kilograms and has an average specific heat of 0.08 kilocalories over kilograms times degrees C. And B. How long would it take to obtain a temperature increase of 2,000 degrees C? And a note here is that the initial rate of temperature increase would be greater than calculated here because the heat is actually concentrated in a smaller mass. But later on, the temperature increase would slow down because you got a 5 times 10 to the 5th kilogram steel containment vessel, which has to be heated up also. So it kind of balances out a little bit. Again, write down what you know. Power equals 120 megawatts. What you're hunting for, the delta T, the change in temperature over time, and they want it in degrees C over seconds. The mass is equal to 1.6 times 10 to the 5th kilograms, and they've got a C. Now, remembering back from last year, power is work divided by time. That means each second, 120 megajoules of work is being done. And from conservation of energy, that means the heat transfer rate, Q, is equal to the work being done. And Q equals MC delta T. Now, we've got C in kilocalories up here. And we can either convert joules to kilocalories, because we've got 120 megajoules here, or get C in different units, which would be an awful lot of research. So it's way easier to convert joules to kilocalories. So here I've got my conversion correctly stated as 1 kilocalorie equals 4,186 joules. And I just multiply it out and I get my kilocalories. And then I plug it into my equation, Q equals mc delta T. And I'm hunting for delta T, and I get a delta T of 2.24 degrees C. But it wants the rate of temperature increase in degrees C per second, not just a temperature increase, which gets it back to our initial statement that the power is equal to work done every second, which means the temperature rises 2.24 degrees C every second. This rate of decay heat will decrease the longer the time is from shutdown. The longer it takes, a couple of days after the reactor shuts down, even a couple of hours, that decay heat slows down. But it's a really real effect, which is why nuclear reactors still need emergency cooling after they've been shut down, which gets us to the second part of the question: how long would it take to obtain a temperature increase of 2,000 degrees C, which is a big one? Okay, so to do that, we're just hunting for the time. We know that the delta T is 2,000 degrees C. So delta T over T, we know from part A that is equal to 2.24 degrees C per second. And so T is our unknown. We just plug in and calculate, and T equals 8.93 seconds or 14.88 minutes. So that's the end of Notes 2. You've got a bunch of assignments to do, as well as another web assign tonight. Thank you very much for your time.